It's particularly a pleasure to be here at UAI in Tel Aviv. I spent my first 30 years, I was born in Israel and spent my first 30 years here, actually in a town north of here, Netanya, similar to Tel Aviv. So it's really cool. I will talk about a methodology and algorithms for anytime probabilistic reasoning. And I will focus on the task of marginal map, which sort of unifies other probabilistic tasks over graphical models. So we all know that task over graphical models, reasoning over graphical models is very hard, and we must resort to approximations, but approximations with guarantees are also hard. So we settle for this anytime reasoning, where we want to provide an answer anytime during the performance, hopefully with some bounds on the error. And if we have more time, we want to be able to produce more accurate results, and if possible, eventually to produce the exact results. So this is the target. And what I will show you is how we can harness the three paradigms, the three primary approaches for probabilistic reasoning, which are variational methods, search, and sampling, to together advance us towards this task. So I will start by some background and talk about the marginal map task in particular, and then go over variational inference methods and their ability to produce anytime algorithms, and how search, in particular and/or search, helps and can then be combined with the variational method within the framework of heuristic search. And finally, what is the role of sampling in all that? And I will conclude. If you have questions, please ask me. Graphical models are everywhere. Here we depict directed graphical models, Bayesian networks, Markov logic, Markov networks, and within their applications of medical diagnosis, character recognition, there is object recognition in vision and many other applications. Also, we can have influence diagrams that allow us reasoning, making decision under uncertainty. Now, the graph that we see here, as you all know, emphasize the fact that there is structure behind these graphical models, behind these models. They are called graphs. And this graph captures conditional independencies between the variables, and this is very, very useful both for modeling and for inference. So one of the most important examples of a graphical model is the Bayesian network. It is defined by a directed acyclic graph between the random variables of interest, and it captures causal relationship, correlational relationship, direct relationship between the variables, and we can quantify. In this particular example, this is one of the earliest examples in medical diagnosis. We have a relationship between smoking and diseases, cancer and bronchitis, and some symptoms. This is dyspnea, shortness of breath, and some test results. And we want to quantify this relationship. It's done by specifying conditional probability functions or tables between the variables. So each child node and its parent is associated with conditional probability, and taking it all together by product, we have a normalized joint probability distribution. So now that we have a joint probability distribution, a model, we can answer any query. And in particular, we can have evidence and ask about the symptoms, and we can ask what is the probability of having lung cancer, and so on. So overall, we can ask queries of prediction, diagnosis, classification, decision-making, and these queries can be expressed formally by applying some operator over the joint probability distribution, like summation, if we want to answer likelihood queries, or by optimization, by maximization, if we want to find the most likely configuration. And overall, in a graphical model in general that can be directed or undirected, we have a collection of functions on small subsets of variables. And let me emphasize that in my talk, I assume that the variables are discrete, and I will not talk about continuous function. If you were in the tutorial yesterday, it was focused primarily on continuous functions, so there is a difference in methodology and in terminology when you're talking about inference in discrete variables or continuous variables, so a side note. So a graphical model is just specified by a collection of functions or factors on small subsets of variables, and they can be taken together by an operator like product. In the undirected case, we have to normalize this product to make it look like a probability distribution. One thing to emphasize is the notion of a primal graph. I will use this graph throughout. There are other graphs that can be associated with the graphical models, like factor graph. But here, in the primal graph, we associate every variable with a node, and we connect any two variables if they reside in the scope of a single function. So in this example, S and D are not connected because there is no function that, a local function that connects them. And here are the three main tasks expressed formally that we normally want to compute over graphical models. The max inference, the sum inference, the mixed inference. Max, we apply the operator maximization for finding them, or the map, finding the most likely scenario or configuration or assignment. In a sum inference, we want to find the likelihood, partition function, probability of evidence, and so on. And in mixed inference, which is one of the focus of this talk, is we need to engage both in summation and maximization in fashion in order to answer the query. And these tasks are all hard, but they are getting harder when we go from map to sum to mixed inference. And just to note here, I think I don't, before I go to the next slide, is that this is hard, but there is one case, one tractable case that makes them all easy. We all know about it, is when the graph has no cycles. When the graph is a tree, we can answer all these queries with a caveat regarding the mixed inference in linear time. And all the methods, all the exact methods, as we will see, they are for answering queries are based on this tree nature. If we don't have a tree, we make the graph close to a tree, as we will see. What about marginal map? Why marginal map? It's actually often the right query. When we have a big system, we are often interested only in predicting the optimal value of a subset of the variables. And this is typical in planning and in diagnosis. For instance, if you want to really find a plan or to find a set of actions, normally you want to sum over the random variables that describe how the world evolves while you are performing the actions, and you want to optimize over the decision variables only. And here I depict an influence diagram, which is the model that you will use if you want to engage in planning. So again, this is a very hard task, and it's not even easy on trees unless the decision variables and the summation and the rest of the variables are organized in a particular way. For instance, here is a formal description of this marginal map task within an undirected graphical model. When we have this model, we will distinguish what are the set of variables that we are interested, the map variables. Here they are the maximization variables here, and these are the rest of the variables that are called summation. And what we want is to compute this quantity. Namely, we want to sum over the summation variable and to maximize over the map variables. Why they are hard, we will see. Okay, so the goal of any time, we really have to do approximations. But we would like to have some information about the error. So we want a bound. still, we want to get answer fast, but if we have more time, we want to trade time and accuracy. So what we wish is to have this transition between time, resources, and the accuracy of our answer. And we would like also to be able to provide bounds that will get tighter and tighter if we have more time. And eventually, if we are lucky and if the problem is not that hard, we want to get an exact answer. So the idea is that we want to develop algorithms that are general, that can be applied in many benchmarks and tune themselves to the problem and exhibit different performance based on what they get. And also, just to help the user stop the algorithm at any time and be able to query what is the accuracy of the answer if he decides to stop at that time. So we will use these three building block schemes to do this type of anytime reasoning. These are variational method. Variational method or inference method, also called sometimes. They reason over small subsets of the variables at a time, and they can also reason about relaxation of the problem, and they are good at providing bounds, but they are limited by memory. Once the memory is exhausted, you cannot extend the accuracy of the bounds. Both sampling and search can aid variational method and get them out of this memory trap. By themselves, these are methods that can stand by themselves and they provide anytime solutions, but by cooperating with variational method and cooperating with each other, we can push the frontier further. So what I will show is how to combine these approaches. I will I will first show how inference can provide anytime reasoning up to a point, and how it can provide heuristic for search, how it can provide proposals for sampling, and the search and sampling can interact. I'm not sure to what extent I'll have time to talk about the last part. So let me go now to inference methods. I think what I will say now is familiar to everyone, but we need to really start from the same on a good footing. So let me just describe to you the main algorithm for inference in graphical model. This version is bucket elimination. In general, you have a collection of functions. This is our probability distribution here. And we want, let's say, to compute this query, the probability of A when we have evidence on E. This is the specification, the description of what we need to compute. So since we need to sum this product on several variables, we do it one variable at a time. So we will collect all the functions that mention the first variable that we sum over B into a bucket, and we will apply the summation to it. And also the rest, all the functions that are associated with C that remain into the bucket of C, and so on. So now, after we do that, we can just apply this sum product bucket by bucket, and we can compute it, and the answer is a function on the variables that are remaining and can be called a message. We send it to the next bucket. Computation is sum product in each bucket, and then at the end we have the answer. So what is at the end? At the end, in the last bucket, we have the probability of the evidence, and we can also compute the answer to the query based on what we have in these buckets. So this is the classical variable elimination algorithm, and you can immediately see that its complexity is not exponential in all the variables, it is exponential in how many variables we need to process in each bucket. In this case, the maximum number is 4, so this would be this algorithm will be exponential in 4. This parameter, the size of the click, is called induced width, and it can be gleaned from just the graph. if we look at the primal graph of this Bayesian network, you can see that the number of variables in a bucket is the number of parents each variable has in this triangulated graph, and this is the induced width, and it's possible. It's also known by the tree width parameter. So this algorithm is both time and space exponential in the tree width and the induced width of this ordering. There are different orderings we can take. They may give us better performance, and the tree width is the optimal ordering over a graph. So all this is very, very, very well known for many, many years, but it's important to state. And also, if we want to solve the map, the only thing we change is that we apply the max operator instead of summation operator, and the algorithm is the same, the complexity is the same, and for many other queries we have the same performance. What about marginal map? I told you that this is what I want to focus on. So I want to focus on this query because it's a relevant query, because it's the most challenging, and because all our work in the last 5 years is focused on this query, and I have new things to really show you about the empirical, about the performance. So here is, if I want to solve the marginal map, here is you have a graphical model with map variable RA, BE. The main thing is that we need to restrict our ordering. We have to apply summation before maximization. Summation and maximization do not commute. So the ordering that we will be able to, we need to use is restricted. But other than that, everything is identically, it's the same. So you place your function in the bucket as before, and for summation variables, the B and C, we will process them by sum product, and for the maximization variables, we will process them by max product, and at the bottom, we will get the actual exact marginal map value, and we can generate now a solution. There is something tricky about that, but that's it's not so straightforward in the case of marginal map, but let's not talk about it right now. And this is again the ordered graph that can tell us what would be the complexity of doing it before we start. And you can see again that here we have to record a function on many variables. And in this particular case, we don't have the liberty of changing the ordering because we must have the summation variables before the maximization variables. So for example, if we did change the ordering, if we just ignored the restriction, we could have an ordering of these 5 variables that would have far smaller induced width of 2. If we applied the algorithm in this unrestricted order, we will get an upper bound. So there is something useful about that, and some algorithm exploited that. Okay, so now that we know how things work exactly, let's talk about how we approximate these and get bounds, and I will talk about the MiniBuckets and the weighted MiniBuckets approximation and how we can tighten them by cost shifting. So the idea of the MiniBucket is very straightforward. We have in each bucket, as you saw, we have many functions. If we cannot process them together, there are too many variables, what we can do is partition them. So in this example here, I'm talking about the maximization. We can just partition into several MiniBuckets and process each and combine them later. What this process does is this function actually it produces an upper bound on the desired quantity, but the complexity is obviously smaller because we process less variables in each MiniBucket. That's the whole idea. And if we want to see how it looks within the architecture of the buckets, here we see that when we get to, when we process the first bucket B, let's say we desire not to have more than 3 variables in a MiniBucket, Then we will partition into 2 mini buckets and send smaller messages, and otherwise we will continue as before, and we will get an upper bound on the map value. So the semantics that can be associated with this process is that we duplicate B and have it 2 names, and it's actually as if we have this, we are processing this graph rather than this graph. So once we did that, we can also do the decoding. We can assign a value. We can find the assignments to all the variables by consulting the buckets one at a time, maximizing the function in the buckets in a greedy fashion, as is usually done. And if we want to look at the bucket and the mini bucket elimination side by side here, this is on the left, you see how the mini bucket will operate when the I bound is 3, and when it will operate exactly, and you can see that the functions are smaller. So the important thing here is now we have a parameter. We can have a parameter that we call I bound, and we decide how many variables we allow in each mini bucket, and this will control the complexity. So to summarize, the properties of the mini buckets, the I give us sort of the anytime parameters. The method is exponential in the I that we chose, and we can know what is the accuracy. We can have a bound. The bound that we get going down is giving us an upper bound. When we generate a solution, we get an upper bound. So we get both a lower bound and an upper bound. And if we apply different levels of I, we will get this kind of the anytime performance that we desire. Let's now, but this is very simple. Sometimes it gives us reasonable bounds, but often the bounds will be quite weak unless the I bound is very high, and especially for summation problems. So we want to tighten it more, and we have ideas from the variational theory. We can just, in this case, we see a graphical model that is we can completely decompose it. So we can, this is a max sum problem, so we can approximate this quantity by bounding it by this quantity as if we are decomposing completely, but instead we can shift some costs for, between the functions. We can add factors that adjust each local term but cancel out in total, and this, by minimizing over these factors that we are adding, we can really tune and get a far better, far tighter bounds on our quantity. And now we can use all the methods that are available. We can apply various gradient descents ideas in order to optimize this quantity here. And this leads to a variety of algorithms. In the literature, you can find these under different names, and they are developed independently in different communities. And the way we use these ideas, we typically we develop 2 types of algorithms that are trying to do this cost shifting. One is iterative, that is applying this iteratively over a joint graph, and can take more time, but can get to the optimal cost shifting. And the other is just to apply it within the bucket elimination architecture, namely to go in one sweep from one bucket at a time, and in each bucket shift costs only between mini buckets. And this gives us improvement, but also can be achieved in a small amount of time. So I will now illustrate this different, how on 2 problem instances, how these methods are working. So what you see here is on 2 instances from linkage analysis in instances. They are pedigree 20 and 37, part of our benchmarks. And you can see that if we apply this mini bucket with I bound, increasing I bound, we get tighter and tighter bounds in both cases. If we do just what we call mini bucket with moment matching, only do local bucket by bucket tightening, we get a huge improvement. And if we allow ourselves iterative more time to really improve the tightness by this cost shifting, we will get additional tightening that will cost more time. So these are, now we have in our, we have several parameters that we can tune. The I, we can decide about the I band, and we can decide about the level of cost shifting that we will do to get the tightening. So what about how all this play out for marginal map? So for marginal map, everything is sort of straightforwardly extended. But now I want to introduce another element that can tighten our bounds further, especially for summation queries. And this is by using the Holder inequality. So this is Holder inequality here. It says that you can bound the sum of a product by the power sum when you have, if you associate it with each MiniBucket a weight, and the weights sum to 1, then instead of applying simple summation, we can apply this power summation, and we will also get a bound. So the messages on the summation variables that we have will now be performed by weighted sum, and on the maximization variables, we will perform the same maximization operation as we did. And this provides us another parameter that we can optimize when we are trying to improve our bounds. Okay, so this is for the weighted MiniBucket. The weights are applied to any summation, can be applied to any summation query. So let me sum this part here. We do have a general scheme that can provide us upper and lower bound in an anytime manner. We can control the computation by the I bound. We can do cost shifting and decide at the level of cost shifting, but it's not really anytime. It's not really anytime because we must stop at some point. I mean, if you have I bound 20, exponential in 20, you cannot push further. If your tree width of the problem is 100, it's not going all the way. So that's what I meant by saying memory is the bottleneck. So we will go now to search and see how search can help us. But first, let me give you some introduction to search or to search spaces and show that also search can exploit the structure behind the graphical model. It used to, in the early days, people thought that search must be brute force exponential, but we know now that it can abide by the same structure parameters that we have for the variable elimination algorithms. So here we have a graphical model, an undirected graphical model, and we could, in principle, organize all the assignments to the variables in a tree along a particular order of the variables. But what we can observe that actually these graphical models, we can organize it into a pseudo tree that capture problem decomposition. We can see that if A and B are assigned, then these two parts of the problems are completely independent, and in essence, they can be solved in parallel. And this is captured by this tree that I have here. So we can actually organize all this assignment, all this configuration along this tree. So here I have the and/or search tree guided by this pseudo tree. It has OR nodes that are variables and their values, and then a variable and values in each layer. So what you see is that after we assign A and B values, we have 4 combinations. We have AND node that route each one of these problems in parallel, and then we continue in the same way. Rather than put C and E in sequence, they are placed in parallel, and this is depicted by this AND/OR tree. Now this AND/OR tree capture all the same assignment, and you can see that it has far less variable nodes in it, and obviously if we search it, it will take less time. The size of this end-OR tree is the size of the tree is governed by the height of the pseudo-tree. It will be exponentially in the pseudo-tree height rather than by the number of variables. But we can do even better and compact the search space further, again, just by looking at the structure and nothing else. So it turns out that often we have redundant subtrees all over. But we can reason and really know where they are by the notion of context. For example, the context of F is A and E. You can see here F, if you know A and E, it's completely disconnected to B. So it means that all the trees below F are only dependent on the assignments to A and E and not on B, which means we can merge these subtrees and have a graph rather than a tree. And we can know that in advance just by looking at the primal graph of the problem. So at the end of the story is this, what we call and/or context minimal graph. The one here is the smallest among the 4 search spaces, and we can just perform apply our algorithms on top of this, and it will be, in this case, examples have 18 nodes, and it turns out that we can bound the number of nodes, again, by a graph parameter, the tree width. Yes? Yes. So, yeah, so this is definitely related. This would be the first step compiling to BDD. We have work that shows how we can extend it to and/or decision diagram. Namely, we can further, by looking at the details, we can further compact this, and you can have, this can be the starting point to a compiled structure, and it's similar to the sum product networks. It seems similar to the arithmetic circuits, and it's similar to OBDDs, but it's more compact because you exploit the decomposition. We have some work on that. So to summarize, we have here now as a graph structure that we can bound if we don't want to really work on the graph, we can bound the size of the graph to be exponential in the height. If we want to work on the graph itself, it will be exponential only in the tree width. And the caveat is that if we search the graph, we will have to use memory. If we search the tree, we will not have to use memory. But as a starting point, this is good. We don't have to do search, exponential search, and we can answer any query on this structure. So just to show you how we do that, because we need to spread numbers from the graphical models, so a little bit, some further details. So we can just spread the numbers from the Bayesian network or a graphical model that we have on the arcs of this and/or tree. Now, a full configuration will be a solution tree, not a path. And the cost of a full configuration will be the product of the values on the solution tree. And we can now define, if we want to answer a particular query, we define the notion of a value. A value of a node will be, let's say we want to compute the probability of evidence, like here. We will associate this value with each node, and we will compute it by recursively from leaves to root. By an OR node will perform a summation, an AND node will perform a product over its child node, and we can search it in any search scheme, any traversal method that we want to compute the value at the root node, which will be the answer to our query. So just to illustrate further, by the way, if we do it on the and/or graph, we will have also to really cache some partial results, so we will not search redundantly redundant subtrees, and this will cost us some memory. So here is just to illustrate, I think on a bigger example, what is going on. If I have this primal graph, this could be a pseudo tree for this primal graph, and this would be the whole search tree. It's interesting to note that variable elimination, the bucket elimination algorithm that I just showed you, is just sending message from the leaves to the root. You can see here the messages along the tree that are actually, it's the bucket tree algorithm. So we can visualize it this way, as if it's going from leaves to root, while search and/or search that I will show next is just performing search in a different way, but from top to bottom. So it's good to realize that search and variable elimination are not that different. They have a different style in which they are traversing this space. And as I mentioned, it's related to some product network and to also arithmetic circuits. So what about marginal map? See, we want to focus on it. Straightforwardly extended. It's just, the only thing is that we have to make sure that in our pseudo tree, the map variables start the tree and the summation variables are coming later on because of this restriction on the ordering. Otherwise, everything is the same. And if, in this particular example, if the map variables were different, like this selection here, we will be restricted to a very unfortunate pseudo tree, which is actually a chain. So we would have a less ability of exploiting the structure in this case. And indeed, the search space will look like a tree and not like this more pleasant, compact structure if we had good ordering. And this is, again, an illustration why marginal web, when you have max and sum, it restricts you. Okay. So let's now go to the main part of the talk, which is how do we harness both inference algorithm and search to help us in the anytime goal. So what we do, we go to the framework of heuristic search. Sorry. So just to take us back to this picture of the bucket elimination. In the bucket elimination, we generate our weighted mini-bucket elimination. We generate these functions, and they provide a bound. And if the I bound, we cannot raise it enough, we cannot improve our bounds. So we want to use search to help. This is one view. The other view is we want to do search, and we want to do heuristic search, which requires a heuristic. So what is this heuristic? If we have this search tree, we can associate every node with a value, with in the case of summation, the sum, the weighted sum below it, or if we are solving optimization, with the optimal solution underneath this node. Now, we don't have access to it, but we are in heuristic search, we will estimate it by a heuristic evaluation function that is an upper bound in the case of summation. Where do we take this heuristic? Normally, we don't know, but in our case, we will take it from the MiniBucket. So that's the main thing. So what is going on is when we computed this function, we computed an approximation on the best cost to go. So if we are now in the search space, and we are assigned two values to two variables, we want now to have a lower bound on the cost. We go to these two functions that were generated, the function that were generated in this bucket and the function that were generated in this bucket, and we get their values, and this will give us an admissible heuristic. We just do table lookup from the functions that we generated before we started the search. And again, this is applicable to all the query, to map, to marginal map, and to partition functions. So once we have an idea, search space and heuristic, we are in business. We can go to the heuristic search community that is old like machine learning community in AI. They have worked hard on really advancing general search anytime, and we can borrow all their ideas and see how far we can go. So for the marginal map, again, it's the same thing. We can run the weighted MiniBucket, and it will be a source of heuristic when we search to solve the marginal map task. Okay, so now we are talking about how to solve the marginal map by search. If we want to solve it exactly by search, we know there is best first search, depth first search. We have the heuristic, we can just apply it. We have a very good understanding of this search scheme. So depth first search is inherently any time for lower bound. It generates one solution at a time that improves, and it can prune the search with the heuristics. It's branch and bound, and that's great. And it can be applied also in linear memory. Best first search is performing in layer of expand the search tree in waves of increasing evaluation function. And when it gets the first solution, it's the optimal solution. Now, it's known that best first search is better than depth first search. It will always expand less nodes, but it requires a lot of memory. We experimented with this, we implemented an experiment with these two schemes, and not surprisingly, best first search was superior. It was superior even because, in this case, even more so than in the regular optimization case, because it requires looking at less summation. It requires less summation operation. Let me explain. So when we are doing this, we are searching only over the map variables. When we get to a tip node of summation variable, we simply compute the sum cost exactly, and this gives us the cost. This operation here at the tip node is very expensive. It's a summation query. Best first search allows us to do less of this by its nature, and it was superior. But we want to move on. We want anytime algorithms, not exact algorithms, because we know that the exact algorithms are not feasible in most cases. So now we looked at two primary ideas from the search community to help us. And one is the weighted best first search. Weighted best first search is the idea that you do best first search, like an A-star algorithm, but you multiply your heuristic function by some constant, let's call it W, and the search algorithm will not be admissible anymore, but when it stops, you are guaranteed to be W away from the optimal solution. So this led to a variety of anytime algorithms that work as follows. You start your best first search with a big W, and it gives you immediately a solution with some bound. And then by some policy, you repeat, you reduce W until hopefully you get to W equal 1, which will be exact solution, and so on. And there are various methods developed in the heuristic search community in order to not to really do everything from scratch. These are given here with restarts, with some repairing, and so on. And all these ideas we borrowed, we implemented, and we experimented with. So this was one class of anytime schemes that we generated. The second is simply the interaction between best first search and depth first search. So depth first search gives us lower bound by its nature. Best first search normally is not thought about that way, but it's actually given us improved upper bound as it proceeds. So if we interact combine these two, we can get both upper bounds and lower bounds. And this is what we did. We developed several ways of interaction between these two schemes, and two of them were performed the best. One is called look ahead, and one is alternating. I will give you some idea about them, very high level idea in the next two slides. Here is one. So the look ahead, the best first with look ahead, is doing the following things. First of all, remember, we are searching and or space. So at any point in time, we have a partial solution tree that we are extending in a best first manner. And what we do in order to really get some solution, we do depth first dives from the leaves of these nodes of the current partial solution and give us some answer, which gives us some lower bound. We do that, we use a control parameter theta to really control the balance between how far we are expanding in a best first manner our search tree and how many dives we do. But overall, we get, at any point when we stop, we have both an upper bound and a lower bound. The second architecture seems very simple. We just do the two searches side by side. So we will have a subtree used by the depth first search and by the best first search that we expand in each iteration, but we also take information that we gleaned from here, from the best first to the depth first, we improve the heuristic, and vice versa, from the depth first to the best first, we cut some of the memory based on what we learned from the depth first search. So I know this is hard to really get the details are involved, but I just want to give you a high-level illustration. There are many subtle things that you need to think through in order to combine these two paradigms, best first and depth first. So we experiment, our evaluation methodology is, since we want really general algorithms, we have a collection of benchmarks, and we just apply our algorithms to many of the benchmarks. This is just for illustration. In this case, we applied it to grid, pedigree, and Promidas, and this table only gives you some statistics about the nature of these instances. Another point is that to solve marginal map, we don't have marginal map instances. We have graphical models. We had to really select the map variable and the summation variable, so we did it in several ways. One way, we wanted to have easy summation problem, and the other, we wanted to have harder, and this means this is what easy and hard refers to here. But let me show some results. So here is just 3 instances from 3 of the benchmarks, and we ran 5 algorithms, 3 of the weighted, from the weighted schemes, and 2 from this interaction of best first and depth first. We have particular 24 gigabyte, and one column is when the I bound that we used to generate the heuristic is in pre-processing was 12, the other was 18. We wanted to see how the heuristic impact all that. I will only, to really talk about it, I will focus on one instance. So what you should pay attention is that on the x-axis we have CPU time, and here we on the y-axis we have the log of the solution. For each algorithm we have 2 plots, one giving upper bound, one giving lower bound, and you can see vividly this is for I equal 12. In this case, the blue algorithms, which are all for the weighted schemes, were not able to almost give us any answer. And here, when the I-bound, the heuristic is stronger, we were able to get results. But it's clear that the red algorithms overall, which corresponds to this best first and depth first interacting with each other, was superior. Here you have a more aggregated answers on one of the domains. We have the best weighted scheme depicted here, and the 2 interacting algorithms, best and depth. And this is another scheme taken from the literature that was unable to solve the problems. And what you see is how the gap accuracy, which is average, is working with time. And it's clear that this scheme is superior overall. But all this work was under a severe assumption. The assumption was that we can solve the summation subproblem exactly. Namely, when we reached a tip map node, we didn't apply any approximation to summation, we solved it exactly. So obviously this is limited to benchmarks where you can solve the summation subproblem exactly. In order to overcome that, we have to go to sampling. So this would be my next a portion of the talk where I will show how variational and sampling can interact and help search. So sampling, and in particular important sampling, we want to estimate normally an expectation, and we do this by Monte Carlo estimate. But often we cannot sample from the function that we want, so we sample from a proposal distribution, Q, and if we sample from Q, we know that, then we will average the weights that we are getting from our samples once we sample from Q, and this is the idea of importance sampling. How do we do importance sampling in our world? One simple approach is just to generate use as proposal the information that we get from the MiniBucket and weighted MiniBucket scheme. If we apply the full bucket elimination algorithm, we will have an exact sampling. So if we have an approximation, let's use it. So that's what is the idea. So what you see here is the results of applying the weighted MiniBucket to, in this case, let's assume a summation problem. This is work by Lee, Fisher, and Eiler in 2015. And now, once we get this upper bound, we can sample from it. We will generate a sample from looking at the function in this bucket, and we can do that one variable at a time. And when we get to the variable B, we will take a mixture. We will sample from a mixture based on these W's, and that's algorithm is called weighted MiniBucket importance sampling. Now this algorithm has a very nice properties. It's possible to show, because we are generating bounds, that the weights are bounded. And from statistics, we know that we can now use some well-known result to get bound. This is a Bernstein empirical bound. We can show they show that actually if we do sampling this way, we get, with some confidence, we can bound the error of the estimates that we have, and this is the error. The error is a function, is reduced as a function of the number of samples that we have, and the bound that we started with, and the empirical variance. So this is really a powerful scheme, because we now have a way of having a probabilistic bound on the summation query. And what we did is we harness it into our marginal map query. So again, when we solve the marginal map, we have a maximization problem and a summation problem at the leaves. This is the part that is very hard. What we will do now is, for each map assignment, we will apply the weighted MiniBucket importance sampling and get an estimate with a probabilistic bound. So this is, again, a repeat of this, of that idea, repeating the results of the bounds for the weighted MiniBucket importance sampling. And now we will have the questions of how many samples to draw and so on. But that's the basic of the next generation architecture that we used. And the algorithms themselves, we again, like in the previous case, we explored several architecture of best first and depth first, where we used for the summation problem this sampling scheme. And here I only show you the results, and two primary algorithms emerged. One is anytime stochastic best first search, so it is based on best first search idea primarily, and the second one is anytime learning depth first search. that is also engaged in some dive into beyond the best first algorithm. I'm not going into the details. I only want to show you the power of this, the ability of this extension to really further us in our ability to solve the marginal map. So what you see here is on grid benchmark, what we see is what is plotted here is the average relative accuracy for each of 6 algorithms, and on the left, on your left, you have the results for lower bound, and on the right we have the results for upper bound separately. And since this is accuracy, lower is better in both graphs. So for upper bounds, so the algorithms that I talked about now, the stochastic algorithms for summation are these two, and the algorithms, the other algorithms I presented earlier. And you can see that these green and the red algorithms are not so good for upper bound. An alternative algorithm that I did not describe is superior here. But for lower bound, these two algorithms are far better than the rest, and most of the time other algorithms, the earlier algorithms were unable to solve many of the instances that we experimented with in this benchmark. Here is another illustration from planning domain. Again, you can see that the red-green are far better than in the case of lower bounds. To summarize, I show you how inference can provide heuristics to search, how inference and a variational method can provide useful proposals for sampling. And maybe in the last minute that I have, I will just say something about the interactions between search and sampling. I didn't know if I'll have time for it, but I do. So what we saw in sampling, 5 minutes? Okay. What we saw in sampling is that we just need a good proposal, and the weighted MiniBucket provides us a good proposal. But we can improve this proposal by interacting between search and sampling. So what you see here is when we are solving a summation problem, we can also do search. We can expand the search tree, the AND/OR tree, and plug in the leaves upper bounds. This is my phone. Upper bound, what do we do? Okay, it will stop.
You can take the call.
So we can, by expanding the search tree and plugging the weighted MiniBucket heuristic and the leaves, we can propagate them up and get much better upper bound. And then we can use, and what we can do is we can use these bounds to sample. So I don't show it visually here, but we can sample from each one of these leaf nodes, but we can sample with improved upper bound because we are sampling from the search tree after we updated and improved the bound. And here, so we developed several algorithms. One is the dynamic importance sampling is the general umbrella name, where we iterate between search to improve the bound and sampling from the bound. And the question there is how much search to do and how much sampling to do, and we developed several parameters and experimented with them. And I will just summarize by showing these are different parameters that control how much searching we are doing and how much sampling we are doing. One scheme, the simple scheme, is just do search up to a point and then do only sampling. And what we show when we want to depict the results is the area between the upper bound and the lower bound, and this illustrates the quality of these algorithms. And this area is what is depicted here for each one of these benchmarks we experimented on, And we see that the dynamic importance sampling with some set of parameters is superior, and actually this algorithm is very nice performance in practice. What do we do with all our algorithms? How we evaluate? What I showed you is that we just evaluate them on benchmarks. We also participate in competitions. There were, over the years, quite a few competitions, UAI competitions. The last one was in 2016. We hope for a new one soon. VBAV promised that we will have one. We normally win either first or second place. Normally, it's with the map solvers. The marginal map was under competition only 1 year, and we won because we were the only one. We have software with all our algorithms, solvers. It's open source, and for continuing work, there are quite a few of parameters that I introduced. We need to know how to tune these hyperparameters automatically, to extend the decision networks, develop languages and tools. We want to extend our algorithms to probabilistic relational languages, and obviously to be able to extend to continuous variables and temporal domains, and find crosswork with deep learning. Finally, these are my collaborators. I mean, what you see on the left is all my students over the years. This work builds on itself one block at a time. So all my students, they really contributed a lot to that. My collaborators for this work is Alex Eiler, Radu Marinescu, which is here. He was my student a few years ago, and my current two students, Junkyu Lee, Chilu, just graduated. Thank you very much.